So in this section, we'll be covering logic verification. We have already covered Verilog for synthesis, in which if we have a design diagram available, how we can write Verilog code for that. Logic for simulation or logic verification is I want to think of it as a totally different way of writing Verilog from writing code for synthesis. For synthesis, we just stick to the exact same syntax that we have covered most of the times. But for verification, we can take a bit of liberty and we can write software style code. So what we do for verification is that suppose you have a circuit that you want to test. We normally call it module under test or device under test or unit under test. Uh, just like you put an IC on a breadboard and you give it some inputs and monitor its output. That's what we want to do, but we want to do it using some software code. So this code won't be used to actually implement the design, but it is a very important code because most of the bugs will be found out by writing this test bench code, which is very important. So for test bench, um, we generally generate inputs for our block and we monitor the outputs. That's the most basic test bench that will be covering it. For more advanced test benches, we generally have some already available reference outputs or a DUT model. For example, I have made my own, let's say I have made my own optimized multiplier, then I can use a model using static and then see whether for a lot of inputs, almost all the inputs do my outputs match. So if there is a model, then we can give same inputs to model as well as to the device under test and monitor the outputs. If there is not a model but reference outputs are available, then we can compare it with the reference outputs. So for example, I want to test the counter that we wrote code for, and so if we want to write a test bench for it, so test bench is also a module, but it's a special module that doesn't have any inputs or outputs because this is because test bench itself gives input to the design and monitors the output. So we instantiate the module that we want to test. For example, we want to test counter. So we instantiate it. Then there are some inputs and there are some outputs. Generally, uh, we declare the inputs as regis and always we declare the outputs as wire. So this I already told you that whenever we instantiate a module, the outputs are tied to whatever variable that has to be a wire. It cannot be a reg. But inputs can be reg or wire depending on how we want to make them. But most of the time we make it reg because we want to use a procedural assignment for assigning these. Then what we want to do is that we want to generate that inputs that will be given to this module. Uh, okay, so we want to generate these inputs and we want to monitor the output. So basically, we can imagine that we want to generate a clock signal and then we want to assert reset for a while so that system is in a known state. Then we want to increment for a while and decrement for a while, and based on that, for example, I increment it twice and decrement it once. So what I expect is that before reset we don't know what the value count will have, so we can show it by x, but as soon as we get a reset on a rising edge of a clock, it should get to 0. And when at this rising edge of a clock increment is 1, so count should be incremented by 1. At this rising edge of a clock, again increment is 1, so it should be incremented to 2. 1 0 is 2. In binary we write 1 0. And then we have in the next clock cycle we have decrement, so it should decrement back to 1. So this is the kind of thing that we want to do in the test bench. So how do we do that? For example, I want to generate a clock. So there is a block called initial block that is normally used for simulations for test benches. So initial is a block that runs only once. So what we do here is we write initial begin end, and we write clock is equal to 0, and forever #5 clock is equal to not of clock. So what does this mean? Forever is an infinite loop, just like a for loop or while one loop. We can also write while one, but forever is a more neat loop for that. So we need that it will always do this thing. And what will it do? #5 means that we want to insert delay for 5 ticks. So every simulation has some ticks. So we don't need to go into ticks at the moment, but whatever tick it is, we want 5 simulation ticks. After that, we want clock to be toggled, that if clock was 0, then it should be 1 now. And after 5 ticks, it should be again 0. And after 5 ticks, it will be toggled again to 1. So we'll have this kind of a signal that will toggle after every 5 ticks. So overall, after every 10 ticks, it will repeat itself. Okay. So forever I've covered, #5 I've covered. So initial is a C style block executing statements sequentially. Unless we move forward in time using hash something or add something. For example, we'll use add pause clock, or we can use add some other signal, pause other signal as well. Um and we can use also wait statement that I won't cover in this talk. So to generate these signals, what we do is that we think of these signals. The time is going from left to right, but we code it from top to down. For example, we write another initial block. There can be multiple initial blocks. You can think of it as just like C, a main function in C, but we can have multiple of those, and all of them will be running in parallel. So unlike always block, which is always running, initial block runs only once, and it runs sequentially. So we want all these signals to be 0 at start. So we start increment, decrement, and reset to be 0. After that, I want to assert reset at sometime after a pause clock. So here I have written at pause clock, and reset is equal to 1. This #1 means that it will be assigned to reset at pause clock, but it will apply at 1 tick delay. So this means that at this pause clock, after a tick of 1, reset will be 1. Normally, we assert signals not exactly on pause clock, but after 1 tick or 2 ticks. Because that's why normally inputs are coming from some other registers and they have some setup and hold time. Uh, so now from here to here, there is no change in the signal. We can see that. But after 1 clock cycle, we want reset to be 0. There is only 1 change. So whenever there is a change, we have to code that change. So we want to spend another pause clock, and now we want reset to be 0. So after that, we want to spend another pause clock, but now we don't want to change reset, but we want to increment. Yeah, we assert increment signal. So again, we can pass time by having a pause clock, and then we can increment, we can set increment to 1. Here I have used a bit of different syntax that I actually prefer, but I just told you the previous syntax earlier. Here I have used at pause clock semicolon. That means that do nothing. Semicolon is a null statement that just spend 1 clock cycle. So we'll come from here to here. And then after that, I have said #1. That means just pass 1 tick more, and then I have said increment is equal to 1. So that will have exactly the same effect if even if I have written this kind of a statement or this kind of a statement. If I haven't used semicolon and I had used non-blocking statement, it will have the same meaning in this case. So but this syntax I normally prefer. Then I want to span 2 clock cycles instead of 1. So one way is that I write at pause clock semicolon twice. But normally, if I want to spend multiple clock cycles, I use this loop. This is also another neat loop. Repeat 2 means repeat twice. At pause clock, that means Um, at pause edge clock semicolon means that do nothing and spend one clock pause edge amount of time. So wait, go to the next pause edge clock and do nothing, and go to the next edge clock and do nothing. This is a constant too. We can also have variables here. So repeat is a loop just like for loop, but it's more neat if we know that we just want to repeat something n number of times. That's it. So since I have written two, so though two clock cycles will be passed. After that, we want to do two things here. We want to transition increment to 0 and we want to transition decrement to 1. So we have done that. We have put increment equal to 0 and we have put decrement equal to 1. After that, we want to spend another clock cycle. So and after that, I want to put decrement to 0, and that's probably it. But I don't want to stop exactly there. I want to spend some more clock cycles to see whether there is no normality in the circuit, there is some unknown output in the circuit. So normally what we do is we spend a few more clock cycles, like repeat 20 at pause edge clock. So I spend 20 pause edge clocks, and after that I can stop the simulation using $stop. So this is how we write test bench. In some of the tools, instead of $stop, $finishes used to stop the simulation, and some tools we use $stop. In some older variants, in addition to that, if you want to display output at console, then we have this printf-like statement. We call it $display. It's similar to printf, except that we don't have to put slash in at the end. If we want to display the value of count, we can say that count is equal to %d, and then we put count, then it will display the value of count. So, so we can use these displays as well to see different values. In fact, we also can use $printf, $fprintf if we want to write a file, but I won't be covering that in this tutorial because this is a basic tutorial. In some older tools, if we want to see this waveform, we have to dump the waveform. So for dumping waveform, we use $dump file, and then we give the name to the file that we want to store these signals in. And to store the signals, we use dump vars, that means dump variables. And here we put the name of the module that we want to dump signals of. For example, if I want to dump signals of test bench only, then I'll write TB. And this variable is actually depth. So one means that only dump the signals of test bench. If I write 2, it will also dump the signal of counter as well. So that will increase the size of the file, but it will have more signals. So these signal views are very useful while debugging. If things are not working, we want to see in the simulation. The purpose of this test bench is to find bugs uh, by uh, by using these simulations before we go to the synthesis step. When we synthesize design and put it on FPGA, we can't see things that easily. So that's why we have these test benches. So in a nutshell, we did 3 steps. We instantiated our device under test. That in this case it was a counter. Then we generated clock. Then we write a main style simulation in which we asserted signals from top to down as if the time was moving from left to right. And if we do it right, then we can see the waveforms using a tool that supports generating waveform. So generally, what tools are available if you're using Xilinx or Terra FPGAs? In Xilinx, latest tool is Vivado. Earlier it was Xilinx ISC. Both have their own simulators that can be used to simulate things. Similarly, with Altera or Intel FPGAs, Model Sim is provided, which is a third-party software which is also commonly used. Uh, for learning purposes, and if you don't want to use GBs of space by installing Xilinx Vivado, its setup is probably around 17 or 18 GBs, and it will take 13 GB of disk space. So if you want to avoid that, you can use some free small footprint simulators like Icarus Verilog, and some online simulators are also available. If you go to edaplayground.com, then you can simulate using Icarus Verilog as well. For writing code, I prefer you can write in any in these IDEs. You can write code in the IDE that has editor as well. But if you but I generally prefer Notepad++. It's also a small footprint free software that can be used, and it is pretty strong, especially column mode and macros that I use very frequently. So I'll be using Icarus Verilog for rest of this tutorial. So if you already have Vivado or installed, I won't be covering EDA Playground, but you can go to edaplayground.com and then try things out. It's very similar to us, and there is a tutorial available online that I'll put a video link in the description. Also to install Icarus Verilog, I'll put a link in the description. But if you want to use Vivado or ModelSim, I won't be covering ModelSim, but I will put another video with using Vivado simulation using Vivado as well. So you can skip this rest of the video if you don't want to use iverilog, but otherwise you can follow it. So if you want to follow Icarus Verilog, you can go to Icarus Verilog download, and we'll have some page that from where you can download and install it. Uh, and once it's installed, it's generally a bin file. Sorry, it just, for example, I think it should be in my, if I go see iverilog. So this is where it will be installed. So so you can run it from here from the bin directory, but it's better if you can set up the environment variables. You can go to properties and uh, advanced system settings, environment variables, and in the path variable, you can see that I have added these two paths because I have installed in C iverilog bin, iverilog in C, so I am using C iverilog bin, and for waveform where there is also another GTK wave folder, and then there's a bin folder. So if I add this to path, that will help me run Verilog from command prompt without going to the exact folder where it is installed. So you can set it up like this way. I'll link a video, some video which installs this Icarus Verilog. Okay, so now I want to cover an example. So I think I have an example somewhere here. I just have code answer. No. Let me see. I think I just made a. Okay, so I have this. Uh, I've made these two Verilog files in Notepad++. This is the same file that we had for a counter that we covered, and this is another file that is the test bench that we have written. So in iverilog or Icarus Verilog, we have this. We have to use this dump file and dump vars to dump things. I have also added a display here to display the count value. So what we do is that, for example, I've made a folder named counter and I've written this code here. What you can do is you can launch command from here or PowerShell here. So I'll press Shift key and then right click. That will enable this open PowerShell window here. So that opens this PowerShell window here. So here if I write iverilog, so it will give me options how to give files or things. So what I want to do is that I want to compile all these files. So there are only two files, so I'll just write iverilog static.v. Uh, I can also give output name. By default, if I don't give any output name, it will still compile them. But if I want to give output some name, so I can write minus O followed by the name like TB counter and then static.c. So now if you see in the folder, I have this TB counter. So to run this simulation, so this only compiles it. To run this simulation, we have to write VPP space and the name of the file. Okay, we don't have to necessarily put it. Uh, okay, okay. Let me see it again. Okay, I'll have BVP instead of BBP. So I will use. Okay, so here you can see that we have this count is equal to 2 printed, which is a promising sign. So, and also we have this waveform.vcd file created because in our code we gave this name to the file. If I want to see the waveform, so I have to write, if I remember correctly, GTK wave. So GTK wave is the other path that we had given. So this is the waveform we had. Here we can open any waveform file. So here I am using this GTK wave.vcd file. And what I can do is that I can add all signals and append it here. So it will just confirm it. And here you can see that this button will zoom fit, that is it will fit the whole simulation in one window, and if I want to zoom it on something, I just click there and just zoom. So initially count value was X because we didn't know what it would be before reset, but at this posage clock we asserted this reset that resulted in count value to be 0. On the next posage clock, since increment was 1, it went from 0 to 1, and then it was again 1 for next clock cycle, and it became 2. Uh, Sorry, I just went too far ahead. And then in the next clock cycle, we asserted the decrement signal. So here's the decrement signal, we asserted it here. At that time, the value was 010, that is 2, but at this rising edge of clock, we had this decrement 1, so it went back to 1. So this is working fine. We can also change the data formats. For example, if I want to see it as decimal, I can have it I can set it to decimal. So now you can see 0, 1, 2, and 1. Uh, if it hadn't worked fine in the first go, I would like to see inside the value, inside the UUT, whether the increment is asserted or not. Since I in the code I have set this value to 1, it is only showing one level deep signals. So if I set it to 2 instead, that then it will also show TB counter signals as well as one module deep, that is any module that is instantiated in TB counter. So if I compile again, so let me clear it, and so I compile it again and then I run it again, and now waveform is again outputted. So I just run the waveform viewer, and now I open the VCD file. So now you can see this plus sign here, and you can see that UUT is also there. So UUT is the name of module. If you go into the code, I have named this module as unit under test. So if I want to add all the signals, I can this recurse import means that it will add all the signals. So if I add them, all the signals will be added. I can select one signal and append as well. So I can, if I don't want to see all the clutter signals, then I can use one by one as well. But in this case, I wanted to add all the signals. Now these are test bench signals: clock, count, uh, increment, decrement, reset. And these signals, which also include enable and mux out, these signals are from inside this UUT module. So this was recursive add append, so it also added signals from UUT as well. Okay, so this way, these waveforms are the main source which are our which help us when things are stuck. When if I don't get count correctly, then I'll go back to the design diagram and I'll see from where count is coming. Count is coming from mux out, so I'll see whether mux out is correct or not, whether enable signal of register is coming correctly or not, and then that will help me identify where the bug is. So that's it for the simulation and verification. I'll cover another make another video for Vivado based simulation.